Welcome back to NANDGAME. We are deep in the software section all the way up to function calls. We are building our way up to making a high-level language, and let's just jump right in with call. The function is perhaps the single most important abstraction in software. A function is a unit of code which takes some input, called arguments, and has some local storage to use for processing and return a value. A function can be executed from anywhere in the program. When a function is called, the address of the call is stored on the stack, and when the function is complete, it returns to the address from where it was called. In other words, when you're writing your code and it hits a function, it'll jump to an address where that function is stored, and then once that function is done executing, it'll jump back to where it was initially called in the code. Arguments and local storage is also stored on the stack. Functions require three segments to work together: a call, where the function is called somewhere in the program, the function, which is the start of the function, and return, which is the end of the function. These three units need to work together according to shared convention of how data is passed in and out of the function. Okay, so our first level call. The call macro invokes a function. It should prepare the stack for a call, jump to the given function label, and afterwards restore the state. Before the call, 0 or more values are passed to the stack. The placeholder argument count is the number of arguments. The calling convention requires 3 shared memory slots. Okay, so I've defined args, locals, and retval, and I've copied and pasted the steps into our code here as comments. So let's just start. Push the current value of args onto the stack. Now I don't think we want to push whatever is stored in register 1 here. I think we want to use that as a pointer to get the current value. And I think we can use our push static macro to accomplish this. So this will push whatever is in the memory contents of the address of that register onto the stack. So we can push static args. Then we can do the same thing here with locals. Push static locals. All right, so the next step is a little tricky. It says push the address immediately after the jump, and this will be the return address. So you can see in our steps here, there's a step that involves jumping. So I think we want to jump to the address after this piece of code here. That's up here. So after this, we want to create a label, and let's call it address after jump. And that label will give us the address of whatever piece of code is after it. So then all we have to do is push that label to the stack, and we can do that using push value, push dot value. Okay, so next is calculate a new args address. Tells us what to do here. So the new args address is the current SP minus the argument counter minus 3. So let's redefine SP as 0 here, since that's what we've been doing, like when we initialize a stack. All right, here's the formula for what we want to do. Let's start by setting A to SP. Okay, then we'll set D to A star. We'll set A to argument count. Set D to D minus A to subtract the argument count. Now we can set A to 3 and set D to D minus A again. All right, so D is now our result, but we need to actually put that. It says calculate a new args address, so we need to set args to what D is. So then we'll set A to args, and star A equals D. And I believe that should be correct. All right, next step, jump to the address given by the function name placeholder. So we can just do go to function name. Here we've got our label, which we used above. Now we have some more steps, which I'll put as comments. All right, so next we have to store the current args value in a temporary slot. So we have to create a temporary slot. Let's see, what are we not using? Are we not using memory address 7? Let's try that and hope that works. So I'll set A to args, put that in D, set A to temp slots, and then set A star to D. All right, pretty straightforward there. Then we restore the locals value from the stack. So we're going to want to pop. I don't think we want to pop memory because that just pops to a memory address that you have on the stack. But pop static should work because that should put whatever's on the stack into an address. So I think that's what we want to do. So pop static locals. Okay, restore the args value from the stack. I think we can do the same thing. Pop static args. Okay, and then we want to set SP to the previous args value. So what we did up here was store that value in temp slot. So we want to set SP to whatever the value is in temp slot. So let's say get A and store that value in D. And we can get SP and then set SP to D. Oops, A to D. Yeah, that's what I meant. All right, and then we want to push retval to the stack. That should be just like what we did up here where we pushed args and locals to the stack. So we just can use push static retval. And that should put our return value of the function to the top of the stack. Okay, I think we followed these directions. Let's try checking solution. And there we go, call successfully completed. That was admittedly pretty hard to follow because all we're doing really is just following the steps that are laid out for us. But all we're doing really is setting up for the ability to use a function. It's complicated, but now that this is done, it's abstracted away from us. We don't have to think about it. We can just call a function now. All right, so next level. Function. The function macro defines the top of the function block. It should adjust the stack to make space for local storage. The size of local storage is given in the placeholder locals count. Okay, so then again, we are just following these steps here. Okay, so step 1, a label with the name given in the placeholder function name should start the block. Just want to create a label with function name. Set locals to the current SP. Define SP as 0. Define locals as, let's see, local should be 2. So we'll set A to SP. Get that value into D. Set A as locals. And then set that value to what we have stored in D. Make space for the locals data on the stack by adding locals count to the current SP value. So all we need to do is whatever this locals count is, we're just adding that value to the stack pointer. So we can do A equals SP again, D equals whatever is stored at the stack pointer, and then set A to locals count, do a little addition, D plus A, and then we got to put that back on the stack pointer. So we set A to SP, now A star equals D. And if we got everything right, this should work. Yep, there we go. Level successfully completed. So just to summarize, all we're doing is moving our stack pointer up. We're adding values to it so that there's space for whatever locals we need. Okay, next level. The return macro defines the end of the function block. It should store the return value in the memory address retval and restore the stack. Again, we have our instructions here really handy. All right, so step 1, pop the value from the stack into the retval memory slot. All right, so we're gonna need to define retval. I think it was 6. Yep, 6. And then we can use pop static because that lets us pop a value from the stack into a memory address. So pop static retval. Set SP to the value of locals. So I've redefined SP and locals here. So let's get the value of locals in D. And then we will put the value of locals in to our stack pointer. Pop the return address from the stack and jump to it. So you should just be able to pop A, so that'll get whatever's at the top of the stack, which should be the return address, into our A register, and then we can just jump. All right, let's see if this works. All right, not too bad. It is easy to just sort of mindlessly follow these steps rather than try to understand what's really going on here. But return just sort of does what it says. Return is at the end of a function. You have a value you want to use. It puts that value into retval, and then it goes back to whatever you were doing before you called the function. Not too bad. Next level. Push argument. Take the current contents of the memory address given by args plus the index placeholder and push it on the stack. All right, first, get contents of args. So we'll set A to args, and we'll set D to A star. Then get index, so A equals index. I want to do args plus index, so that would be D equals D plus A, and then push it onto the stack. So push D. Check solution. Guess that doesn't work. So the expected number was 42. We got a bigger number. So that's probably a memory address. So maybe we're not supposed to push D directly onto the stack, but we're supposed to get the value that's in this memory address and then push that to the stack. Let's try that. There we go. So this refers to a memory address, and we don't want to push the address. We want to push whatever value is in that address onto the stack. Next level, pop argument. Take the value on top of the stack and store it at the memory address given by the value of args plus the index placeholder. This might require using a temporary memory slot. Okay, so to make it simpler, I've written out some pseudocode, and I've gotten our variables added up top here, args and temp, which you're going to need. And I've just used these memory addresses from previous macros. So first we want to get the value of args plus index. So we're going to set A to args, and we're going to set D to the value of what's in args. We're going to set A to index, and then we're going to save args plus index into the D register. Next, I want to get the value on the top of the stack, because we're going to have to put that value into the memory address we just computed above. So we can do that really simply by doing pop D. Of course, you can see the immediate problem is that we overwrite D here. So that's where we get around it, by storing D in our temporary memory. So we'll set A to temp, and then A star to D. So now we got that stashed away. And this pop D macro also overwrites what's in our A register, I believe. So you can see that here, we're overwriting what's in the A register. We're using that for this code here. So in order to store the values back, we actually have to set A to temp again. And then we want to set our A register to the memory address, the pointer that's in our temp register. And then we want to set that to what we now have in our D register. Okay, let's check solution. Some level successfully completed. We're doing some juggling here, which makes it complicated. But again, as long as you can just follow the steps and really try to take it just a piece at a time, it's not too bad. And hello from the future. I actually have just finished function calls and realized that my explanation for add is convoluted. So I'm going to redo it. Because where I had explained how everything was working under the hood, we really just built everything under the hood. And so we don't really need to understand it anymore. We don't need to know how the function, return, and call macros work. We just need to know how to use them. How do we write a function? Now, first over here, it just mentions how functions are very important to programming. An add function like this, maybe not so useful because it's pretty easy to add numbers in our normal assembly code that we've been using. But when you have things like multiplication, division, or other things you want to do, like checking palindromes or doing some other text parsing, functions allow you to write the code once and then just reuse it. And it's generally just more flexible than our assembly language because we can call it with a certain number of arguments very easily. We can use local variables very easily. So this add function that we're going to write is really just showing you how to use functions. Now, my first attempt at this, I actually did it completely wrong. Because if you look at this test code, it initializes the stack, okay, and then it pushes two values to that stack and then calls this add function. So I thought, okay, we're pushing two values to the stack. All we have to do is pop D, pop A, and then add those two together. D plus A is put that into the D register and then push D back onto the stack. And I've also defined args here. This doesn't work because it ignores the function pattern that we've actually just gone and programmed. So if we check solution, yeah, it's not working. We have to just remember that function, return, call, these macros are doing a lot of heavy lifting. So when you call this function with 2, it's going to set the last two things in the stack, the things you've put here, into that special spot in memory for our arguments. So we're no longer going to find these values on the stack like this. Possibly the easiest thing to do, though, is actually to push them back on the stack. So we have push argument 0, so it's 0 index, so that'll be our first argument here. And then we're going to push argument 1 to the stack, and then we can pop A, put this in the A register, and we can pop D to put the other argument in the D register, and then we can set D to D plus A. Push D to the stack, and then this return at the end here just returns the solution to that retval area in memory. All right, so let's try this. Oh, and that doesn't work because if we remember, this pop D macro overwrites the A register, so we just have to reorder this. Try that, and there we go. And then the other thing we could do instead of using these push argument macros, we could do something like this, which accesses the arguments directly rather than pushing them on the stack. That's probably a better solution in terms of efficiency, but I think this explains what's going on a little bit better. Okay, so let's go to the next level. And this is subtract, so we have to write a subtract function. It's probably a good idea to rewrite this just like you did with the add function, but it really is the same thing pretty much. So if we go back to add, copy that, we're just pasting it into sub, changing our little note here, and all we got to do is subtract here. Instead of d plus a, we do d minus a. Now we've got a few errors in the code. I guess we don't have to define args again, and we actually have to change the function name to sub instead of add. Okay, let's check our solution now. Oh, and actually we've subtracted the wrong way, so we need to change the order in which we're pushing to the stack. Let's try that, and there we go. So minor modifications to our add function, and we have subtract. Okay, negate. Arithmetic negation of a number. So if we have 7, we just need to turn that into -7. Seems pretty simple, so let's set a to args. And then we want to set a to where args is pointing at, and then set d to that value that pointer is pointing at. And then we can just do d equals -d. And of course we have to push that onto the stack. Okay, let's try that. There we go, pretty simple. Once again, we're just accessing arguments and getting the value from the arguments. And then we're doing what we need to do here, which is just turn it negative. Once we got that, we just push to the stack and we're done. All right, next level, getChar. Wait for the next keyboard input and return the key code on the stack. The keyboard input is memory mapped to address 6000. The function should return when the key press ends, i.e. when the input changes back to 0. All right, so the first thing we're going to do is define key as 6000. Get that variable name in there just to make life a little bit simpler. Now this function doesn't have any arguments, so we don't need to access args at all. But we should start by setting a to the key. And let's set our D register to the value that's in the key. So then we want to check if that value is equal to 0. If it is 0, we want to go back to the beginning here to keep checking until our key press has changed. So we have to create a label, call it listen, or let's say listen start, because we might have another listen function. So then if we start the function and it's equal to 0, we just keep looping and looping and looping until it changes. Once it does, we'll go to this next line here, and then we will push whatever that value is to the D register. Then we're gonna have to listen again for the key to change back to 0. So let's make another label called listen end. We'll get the key, we'll put the value of the key in the D register. And this time, if D is not equal to 0, then we wanna jump to listen end again to keep listening for that change. And if it is, then we just return. So let's try it. Okay, maybe this is supposed to be a hex value. And let's try that. Oh, there we go. So it was hex address 6000, not 6000. Okay, so I've commented this to make it a little bit easier. I opened a GitLab account to publish these solutions. So if you want to look at them a little closer, then you can do that there. I'll put a link in the description. But again, pretty straightforward, just a couple different loops where we're waiting for keys to change. Okay, final level, putChar. Send a character to the electric typewriter. The typewriter input is memory mapped to address 6002. The function takes one argument, the character code, to send to the typewriter. So let's define char as address 6002, and that's hex address that we learned from the last time. We're going to grab the args. Of course, we need the address that args is pointing to, and then we can put that into our D register. So then we just have to put whatever's in our D register into this char section. So we can use this pop static macro to do some of the work for us. You want to push the D value and then pop static to the char address. And that should work, though I wonder if our solution will cause a problem. Let me try it. I don't think this solution will work just yet. Let me try it. Oh, it does. It actually does work just fine. Now I was thinking we're gonna have a problem if we don't put something to the stack, because usually when you write a function that doesn't actually return anything, maybe you want to push a value of 0 to the stack just to return 0. Hey, this function worked. In fact, let's check that. It still works if you do that, and that's probably better, just so this function actually returns something. In fact, without it, I'm not really sure what the function is returning, if it's returning something it maybe shouldn't. But I'm going to leave it like this because I think this is actually better. Okay, that's function calls. That seemed like a complicated one. That took a while, but we've got the setup for our function, and I think we now understand how to make functions, how to write functions, which will make programming in this this sort of upgraded assembly language a lot easier. But up next is high-level language. We'll see how that goes. It looks like a short one, but I have a feeling this is going to actually take quite a lot of time. But well, you know, we'll find out. See you next time.